So, galactic recycling. So a galaxy, so what is a galaxy? A galaxy is a group of stars. So they're basically saying those stars in which galaxy are we in? The Milky Way galaxy, like 100 billion stars. And those stars have kind of come to be through this sort of process. You're like, which came first? Well, I don't know. Let's see. Let me kind of pull up my thing. So the caption here says, a star returns material to space when they die. Okay, so we'll call that 1. Number 2 up here, this actually is a star that wants to be. Can you kind of see the jets of energy? Okay, that actually is kind of what we call a protostar. Okay, so it's not settled down yet. And this actually is the star when it's settled down. So I'll put a 3 there. Stars live their lives then, and they die. We're going to talk about how stars die. We'll talk about how our sun is going to die in about another 5 billion years or so. So we're okay. Yep. So as we talk about the formation of our solar system, we're going to refer to it as the nebular theory. So guess what? The nebular theory. There you go. The nebular theory. All right. So kind of from left to right, does this look like a nebula over here on the left? Okay. And what these arrows are trying to show is a bit of contraction. I like this figure down here. I'm kind of a picture person. What it's trying to show you is a bit of contraction, more contraction, and actually the blue lines, what is the blue lines here showing us? What are these showing us? Rotation, exactly. Not all stars do that, but if they're going to have planets in orbit about them, they got to kind of have that rotation going. So it doesn't all collapse into one object. That rotation kind of makes it into a frisbee or a record. Okay? So it's kind of in my imagination, I can see this actually in the region in the center will be the sun, which is what it ends up being, and kind of in the region outside, it's kind of a flat disk, is going to be the planets. Okay? Very good. And there's a lot of physics in this, actually kind of for it to go like this and squeeze in and start rotating. I mean, actually, there's physics of gravity involved and kind of conservation of, well, we talked about potential energy and kinetic energy. Which one's the energy of motion? Kinetic, yeah. So basically, as it's out here, it's got a lot of potential energy. As it kind of squishes in, it's got less potential, more kinetic. So that's kind of associated with the angular momentum you see in the rotating and everything. Okay, so that's kind of generally how it goes. So these are actually, and I'd have to double check, but I believe these are photographs. Okay, we do a lot of, the ones we saw before were like artist figures or scientists drawing, you know. This is actually a photograph of a star and in the throes of kind of being born. So a lot of times if you look at this sort of topic, the photographs are going to basically kind of block out the middle object because you don't want to focus on the star. Okay, stars are kind of oozing energy that kind of throw us off. I'm thinking this is how it works. Let's see, yeah, infrared emission. Do you remember on the figure we saw starting out today, the kind of the jets of energy? Okay, so the jets of energy are kind of perpendicular to the plane where planets can form. Think of it that way, okay? Does our sun spin, rotate on its axis? Yeah. Is it, how many? It's a month. I think it takes about 28 days for the sun to spin once, okay? And you can see the sun spinning if you go out and look at the sunspots move, okay, because they're, anyway. So part of the reason that we come up with this idea of how did we get to be who we are as a solar system is by looking at other stars doing the same thing. I just think that is so exciting.
Why is it, so the infrared picture, it's just got the two, shouldn't it be like everywhere?
Well, he's asking why is it kind of confined to the jets? That actually, I think, has to do with kind of the rotation and the energy shooting out at the poles of This is not a star, this is a protostar.
Oh,
Yeah, so it's not a full-fledged star. And infrared, remember, is infrared longer or shorter than visible? Do you remember? Longer wavelength. Longer wavelength. Yeah, infrared's longer wavelength, exactly. So we kind of talked about different astronomy, and this is actually just kind of looking for that. It's a thermal signature. It's a heat signature. Yeah. I don't know if that answered your questions. Well, your question, but okay. So this is early on. Our solar system is not formed here. Okay. 200 AU. Now, what's an AU? Astronomical unit. And what distance is it? Yep, the average distance between the Earth and the Sun, exactly. So 200 AUs is way out there, okay? So remember I said a minute ago that basically we started a nebula and the nebula contracted and started spinning and that sort of thing. This probably would be at the point it's contracted a little bit and it's spinning. All right. So we're going to talk about how those planets formed in this nebula. And being here from the Midwest, how many people in here have ever made a snowball before? Yes. I really think of it kind of like a snowball. Okay, it's a gravity thing, it's a maybe even electrostatic thing, but basically over about 100,000 years, the stuff that's swirling in this disk around what became our sun kind of picked up its stuff and kind of made it something bigger. Okay, but there's a little bit of a catch. So, you guys remember I said what are comets made of? What are their rock and ice? Literally H2O ice. Okay. So what temperature does ice freeze at? 32 Fahrenheit. Very good. Do you guys buy this? That if I get too close to the sun, especially early on, let's say I'm 100 Fahrenheit. Is your water going to, actually at 212 it boils, right? So let's make it 300 Fahrenheit. Okay, your water is gas. Okay, let's go ahead and get farther from the sun. It cools down. Let's go ahead and get 150 Fahrenheit. Now at that point it's supposed to liquefy, right? Okay, let's go ahead and get out here where I'm below 32. Let's say I'm 20 Fahrenheit. So finally it's going to freeze. So that kind of proximity to the sun, okay, which wasn't the sun yet, but it's still warm over there, okay? That proximity to the middle of our solar system actually kind of is a player in how the materials can freeze and become part of a planet, or a comet, or an asteroid, or a Pluto, okay? So stuff out here, okay, is going to have different composition. So you see that frost line there. That frost line kind of differentiates. These are my rocky planets, right? Yep. And these are my gaseous planets. That frost line is kind of a break between, well, here's one for you. Do you guys buy this? That metal, how do I say this? You can take metal and heat it up way pretty high and it will still be a solid. Okay? So I'm on this side of the frost line. Metals can go ahead and down here, that's what this is telling you. Down here, what temperature do they melt at? So that means anything this temperature or cooler, they're going to go ahead and solidify. So our inner ones were made of kind of things that could go ahead and solidify at high temperatures. Okay? To get your ices, you had to go out over here. That's kind of how.
so does that mean maybe Earth went into the frost line?
There is definitely discussion out there, and it's been out there for a while about did our planets kind of migrate? Oh, no, I think I know what you mean. Why do we have all of our water?
Yes.
Okay, that's a slide coming up, Ty. But actually, it's a little more complicated than I'm describing it. Early on in the formation of what's going to be our solar system, there was a bunch of leftovers, a bunch of random crap that wasn't orbiting the sun. It was kind of going randomly. And so actually during that time, we had stuff come from the outer, kind of what you were saying, stuff like rocks, big rocks, maybe even the size of almost of a planet themselves, kind of coming randomly in and hitting planets that was going to be planets like the Earth. And as they did that, they brought their ices with them. And so then the ices became part, or the water anyway, became part of the Earth. Very good. So, but if we go with the whole frost line, or if we go with, this is part of the nebular theory, I guess I should say. The idea that there was a kind of a demarcation where out here you got your gas giants, in there you have your terrestrials. We call that kind of demarcation the frost line. Oh, I got to tell you this. This is totally not this slide. But remember we were talking about kind of doing something with like cleaning up Pluto's orbit so he could be a planet. Yeah. So that podcast that I posted, that Star Talk podcast, it talks about, and I kind of knew this, but NASA has a thou shalt not mess with the planets. It's called a forward and backward sort of, don't screw with the planet and don't bring anything back to Earth that might screw up Earth. So I think we can't do that.
It's not allowed.
It's not allowed. On the thing I was listening to the podcast, it was so funny because I mentioned that if we're going to visit Jupiter, we're going to have a hard time because you can't stand on Jupiter. But Jupiter has some great moons that orbit it. We just go stand on those, okay? And this one was talking about Saturn. And Saturn has some great moons too. And so the guest was talking about Enceladus, which is a moon around Saturn, and said, well, Enceladus has liquid oceans. And it does, underneath an icy crust. That's cleared by Saturn, liquid oceans. It's amazing. So anyway, so the other host was saying, well, why don't we just go out there and throw in some microorganisms into that ocean? Yeah, and let them grow, let them evolve. So it's like, yeah, but that is so neat, though. I don't know. If there are aliens, check out Enceladus. I think there's a movie about that. So anyway, kind of from left to right again, you can kind of see the thing in the center is going to be our sun. Now this is early on, okay? Clear over here, finally at the right, you see our solar system. Okay? Now, can you see like the crumblies that I was talking about? And here's a potential for actually rocks to come in and hit the planets. Okay? And I mentioned snowball. Doesn't it look like a snowball thing? You just kind of go ahead and make it bigger and bigger, collect your stuff. I think that is so cool. Now, the word you're going to need to know for the test, starts with the letter A, is accretion. Okay? We call that process of kind of snowballing accretion. And another thing sometimes I kick on the test is the word planetesimal. I just think it is so adorable. So planetesimal is a not quite planet yet. It's like a budding planet. Is it possible for two planetesimals to combine and make something larger? Yeah. Yep. Okay, so that's kind of how that works. There's, more to it, I'm sure, but that's the gist of the idea. Now, this is kind of, as I've been doing it, that's the sun. This is the frost line. So we Mars. On the frost line, kind of think of, that was the other thing that was on this podcast. On the frost line, kind of think of the asteroid belt between Mars and Jupiter. And one of the things, and I'd heard this before, she said, is if you take all of the stuff that is in this asteroid belt and combine it together, it wouldn't be the size of a planet. I think it'd be like maybe the size of our moon. Okay, so somebody's like, oh, well, maybe that's just a planet that broke up between Mars and Jupiter. So we go back out here. Now, one of the things, do the gaseous planets, do they have moons? Do they all have moons? Yes, they do all have moons. Okay? And this right here, this little swirly thing, think of it as Jupiter. Basically, if I'm out here, Jupiter, okay, this is part of the nebular theory. In the formation of our solar system, we have this swirl around the sun, but we also have this swirl around Jupiter. Okay? And that swirl actually is responsible for the snowballing we talked about, to create those awesome moons around Jupiter. So each kind of little planet out here, anyway, has kind of a swirl of stuff around them that ultimately forms into their, did I say planets? Moons. That forms into their moons. Yeah, I meant to say moons. That forms into their moons. Okay? Each one of these. I think that's cool. It's like a swirl within a swirl. And what direction is that swirl going? Counterclockwise. Yes. And the Neil deGrasse Tyson it's a right hand rule basically. If you kind of take your thumb and that your thumb is the axis of rotation and you go like that, that's how it is. You know what I'm saying? Okay, right hand rule. Counterclockwise. So go Neil. All right. Now this kind of talks about when we talk about the planets. What's the symbol for helium? 2 letters. He. Very good. What's the symbol for hydrogen? H. Very good. So they're pretty darn light. Okay, hydrogen and helium are very light. But out here, when the snowballs started getting big enough, actually they created the gravity that was sufficient to keep those gases as part of them. That is so cool. I think that is so cool. All right. Okay, so now you read this from the top down. Does the top kind of look like a nebula? You see the nebula getting smaller. You see the nebula spinning and flattening out. Okay. Now, one of the things that happened in the center of the nebula, the solar nebula, okay, the center's going to be the object that's ultimately become our sun, is that object got more and more compact, okay, it gathered more stuff to itself. Gravity was sufficient to go ahead and not only the metals, but also the hydrogen and helium became part of that object that turned on to become our sun. So we'll be talking more about the birth of our sun, but I don't know, can you see the difference between these last two? I call this one A and this one B. What would you describe as the difference? Let's see what color will show up. I'll call this one A and this one B. What's the difference?
All the gas.
All the gas, yeah. And the difference between those is, dun, dun, dun. And I go, that's my solar wind, okay? So if I'm the sun here, okay, I'm the proto-sun. Proto means it's not ready yet. Okay, I'm kind of cooking. I've probably got jets of thermal energy coming out perpendicular to my disk where the planets are forming. But finally, I get hot enough in my core, only in my core, because stars don't do this on the surface. I get hot enough and enough pressure in my core to basically take my hydrogen, fuse them together, 2 hydrogen atoms, which is incredibly difficult, to make 2 hydrogen atoms basically coexist, squish them together, and they become helium. That's called nuclear fusion, and when that happens, a small amount of matter is converted to a lot of energy. Okay, so that's nuclear fusion. That's what happens that's what's happening in the center of our star still, in the core. So anyway, when I do that, and I think that would be so cool to be here when that happened. Oh my gosh, because it's just I think it's got to be pretty quick, yeah, pretty quick. So all of a sudden, I'm just going from being nice and toasty to basically, with that nuclear fusion going on in my core, I am creating energy. I'm shining, like totally bright, okay? Shining in all directions. And with that shine, with that energy, comes literally a positive pressure up. It's called solar wind. All stars have it, okay? Solar wind. It is so cool. And we were talking about, how do I say this? Stuff coming into our solar system. And a germ or something actually would have to go against it would have to float against the solar wind that our sun is creating all the time. So I say that, and that's actually the difference between A and B, is the solar wind kind of took the gases that wasn't part of a planet, wasn't part of a comet or a asteroid, and it basically flashed it off. It's like, dude, you're out of here. So I think that is so cool. Solar wind is neat. Okay, so there are some dates, a few dates in astronomy that I need you to know for the semester, and this is one of them, 4.6 billion years. So the solar wind, the turning on, the begin nuclear fusion in its core, that happened about 4.6 billion years ago. And there are a few ways to date that, and I'm going to talk about one way at the end of these slides. It is so cool. Okay, in Unit 3, we're going to kick off Unit 3 talking about the leftovers, the stuff that's that didn't get blown away from solar wind. It's heavy enough for that. But the crumbly stuff that never became a planet. Of course, there's a lot of crumblies between Mars and Jupiter. We call that the asteroid belt. Okay, there's a lot of crumblies, and we'll be talking more about this. What is, starts letter K, what's this out here beyond Jupiter? Or not Jupiter, I'm sorry, beyond Pluto. Kuiper belt, yeah. Like Pluto is actually kind of in the Kuiper belt. Okay, and then starts letter O, what's this? Oort cloud, yep. Okay, so those are crumblies, right? We'll be talking more about that. This actually gets to what Ty was talking about. This is kind of talking about early in our solar system. Do you remember a few slides ago we kind of had from left to right? Over here was a really busy, lots of crumblies. Then we had our planetismals. Planetismals can combine. Sometimes they say they form protoplanets or planets. Okay, but we had a lot of crumblies, a lot of opportunity for collisions. Our moon, do we see some craters on our moon, right? And those craters are from collisions. And a lot of those collisions from our moon was early on in our solar system. I'll go ahead and point to this, though. This is actually when the sun is turned on. There's still crumblies kind of roaming. It's like I've heard it called if you've ever played, you get in a car and you try to hit other people with your car. Chicken. No, chicken. But like... This is like at Adventureland. Yeah, Derby. Bumper cars. Something, chicken sounds scary. But that too. They did. I didn't like that part. Yeah, I don't like the whole chicken thing. But yeah, Derby, like crash 'em up Derby. That's kind of what things were like. And this actually talks about the water. That water, bless you. They think that actually most of the water that's on the planets actually came from out here. It was a crumbly out here. It solidified. That crumbly came ramming against things. Okay, and one of the things it rammed against was the Earth. Okay, and it struck the Earth and brought its water with it. Yeah, I'm so glad there's enough room up here to walk back and forth. Okay, what else we got? Remember I said Mars has 2 moons, but they look like potatoes? Meet the potatoes. Don't they look like potatoes? Do they look like Earth's moon? No. They're called Phobos and Deimos, means panic and fear. So, like somebody was creative. And they have kind of, they're rebels in that actually... The Phobos and Deimos orbit Mars clockwise, not counterclockwise. Like our moon is obviously counterclockwise. The Earth spins counterclockwise. The moon rotates counterclockwise. But these actually orbit their planet clockwise. And it's thought then that they were probably just kind of crumblies that got too close to Mars and has been with Mars ever since. Gravity kind of said, hey, why don't you be my moon? Okay? Phobos and Deimos. So we're into the exceptions part. Remember on Wednesday, I said we need to come up with a theory of the formation of our solar system that explains what it looks like now. Okay? And this is one of the kind of exceptions. Why do we have Mars, a planet that orbits the sun counterclockwise? And around Mars, the Martian moons go clockwise. And here's your explanation. They were probably captured. Okay. What else do we need to explain with our observations? Well, an anomaly, and I think I might have mentioned it Wednesday, what we shouldn't have that we have is our beautiful moon with a capital M. And we're hoping to see that on March 1st over there on the hill. Okay. That's our next lab.
You don't have that Wednesday night blizzard one scheduled?
No, that was a secondary lab, I think.
Okay.
So, and if the first one goes, which it did, the second one does not meet.
Okay.
So we're crossing our fingers. March 1st, it's supposed to be, I think there's already a forecast out for that, but it's supposed to be kind of cold.
Okay.
So wear layers, I heard somebody.
Yeah.
Yeah.
Don't walk back to the car and get almost attacked by demons.
What's that?
That's the last time I had to go get my coat from the car and was got attacked by some demons.
Some deer, yeah, watch out for
They're
those
running
deer.
at me.
Yeah, they are so pretty though. They came running at you?
Yeah.
Dang,
And the one was just staring at me. I'm just like, I'm not moving.
that's a good idea. But there were deer up there. They're so pretty, unless they're attacking you. So Earth's moon is totally not like the Martian moon. And you figure Earth couldn't have its little kind of little extra stuff like these guys had out here, okay, because these guys are massive and they had actually cooler stuff. It was cooler out here. They had access to more stuff. So they think that actually, and I've heard the word Thea before, an impactor, on this figure, the impactor is orange, excuse me. Okay, here's the forming Earth, okay, and the impactor hits Earth and then goes about its business, but in the meantime, basically part of Earth is splashed out, kind of crumblies from Earth is splashed out, orbiting the Earth, and then there's time for those crumblies to reassemble to form the moon that we know and love today. So it's kind of, sometimes it's called the collision ejection sort of theory. So as the Earth spun, then the young Earth spun, so also that kind of debris of material that came from it, spun around it. Yeah. And there's a couple things why this makes sense. One is, well, I won't, how do I say this? There are some people that don't think we ever landed on the moon. I personally think we did. So we actually have visited the moon, I can't remember how many times. I think we should go back to the moon and land on the moon for good practice and all sorts of reasons. But anyway, while we were on the moon, we actually brought back some rocks from the moon rocks. And as it turns out, the composition of those moon rocks are very similar to what Earth's crust would have been at the time of it getting hit. So basically, it was the crust part that went up and formed the moon. And then I was listening to this on the podcast. The other thing about the moon is that it doesn't have the heavy elements like a planet has metal in it. The moon doesn't. So that's consistent with, it basically was a part of the forming Earth. It's kind of the light stuff on Earth. Okay. What else we got? So that explains the moon. We talked about Martian moons. We talked about Earth's moon. Another thing, and actually kind of comes along with the crumblies, impacts and all that, we need to talk about why some of the planets do the weird things they do. So, for instance, Wednesday, I brought up that chart, remember? And we looked to see the axis of rotation, how much it was tilted.
Yeah.
Do you guys remember how much the tilt was for Venus?
It was like 177.
Yeah, it was like maybe 177?
Yeah.
That sounds right. It was basically like that. Okay? Yeah. And so, although Venus, and sometimes I have to concentrate, make sure I'm right on the right page, although Venus orbits the sun counterclockwise, am I going counterclockwise? Yeah. It spins on its axis clockwise, which is kind of weird, because all the other ones go counterclockwise. Okay? And like this slide says, why did that happen? Well, it's probably that it got hit by something really pretty darn large, and basically hit enough that it twisted all the way around. I can't picture that. A similar thing, so what comes after Saturn? What? Uranus, yep. Comes after Saturn, Uranus. And Uranus, if you ever see its axis of rotation, actually it's lying in the plane of the ecliptic, basically. Okay? And I just think that is so cool. So if that's the sun, it kind of goes like this. It spins, on its axis, but it goes like this. And it just kind of, I think that is so cool. And again, it was an impact that made that happen. All right. So like I said, well, first off, how long ago do we think that the sun began? 4.6 billion years ago, right? 4.6. A lot of times in astronomy, you'll just see a B for billion, YA. Okay? 4.6 billion years ago. Oh. So you're like, how do we know that? Well, there's a few reasons to know that. And one of them actually is to, make sure I get this right, is to look at kind of the pristine, how do I say this? Well, I'll do it this way. We talked about falling stars, right? Okay. So a falling star is basically a chunk, a space rock falling through Earth's atmosphere. And I kind of butched this up a little bit, but it's on the slide. What do we call it if there's something left to pick up?
Meteorite.
Meteorite. Very good. ITE, meteorite. Yes. So if we have a meteorite to pick up, that's a space rock. And actually, these are great for understanding our solar system. We can take a meteorite and we can look at, anybody know what the symbol for potassium is? What letter is it?
Okay.
K. Very good, special K. What is the symbol for argon? 2 letters.
It's AR.
AR, very good, okay? So you kind of see potassium going down, okay, and argon going up. Now, this is the opposite, I think of in a way, of nuclear fusion I talked about. In stars, basically you take hydrogen and hydrogen to go to form helium. What the elements will do, what argon will, bless you, what potassium will do over time is decompose, basically, split up, and it will form something lighter, argon. Okay? And that's really, it works well for a clock then, because kind of you see those curves up there, scientists know the time at which this takes to happen. So we can take our space rocks and we can look at the amount of potassium, the ratio of potassium to argon, and we can see how much potassium was converted to argon, and we can date those rocks. And we're coming up with 4.6 billion years ago those rocks were formed. So 4.6 billion years old is how old our solar system is. Here on Earth, actually, we have rocks that have been here 600 million years after the formation of our solar system. Yeah, so 600 million, excuse me, final answer, 600 million years. Yeah. Oldest rocks on Earth, 4 billion. Moon, part of the Earth, right? You're looking at they can be dated back to 4.4 billion years old. And this, my friends, is a space rock. A space rock that's been kind of cut so you can kind of see some of the detail in it. There's 3 different types of meteorites. I'm not good with meteorites. Sometimes students will bring a rock to me, or they'll be like, Mrs. Snipes, is this a meteorite? And I'm like, I don't know. But I know that you can send it away to get it tested. Okay. Was that the last slide? Mm-hmm. Oh, I looked through that. Oh my gosh. Any questions? Okay. So sorry for talking so fast, but it's also wonderful. Have a question, Julia?